Welcome back. Before I start return talking about physics in the real world, just a reminder, the first problem set is due September 6th, which is a Wednesday. I'm trying to have the problem sets due on Wednesday, part so that they're not immediately preceded by the weekend. And I have my office hours hopefully strategically timed on Monday afternoon and Wednesday morning if you want to come and talk to me about the problem set. That's totally a good thing to do. About the problem set, it covers material that we're currently covering on through the story of ramps, which we'll get to probably start on Wednesday and finish hopefully on Friday. So the material will build up. I do encourage you to look at the problem set in advance. You can do it. I've set it up. It's on Colab for many reasons, and I've set it up so that you can complete it twice, which means you ought to be able to get a pretty decent score on it. But don't guess on it. It's a waste of the whole process if you just play guessing games or if you farm out the work to your friends. The point of it is to have you thinking about some of these questions, and it will solidify your understanding. Passive learning, particularly for physics, doesn't work very well. So yeah, you can go listen to me jibber jabber up here, but it's far more effective, first off, if you get engaged, and I really appreciate the questions last time, keep it up. And if you get to facing the problems yourself, I mean, that is where you finally have to learn the material, or teaching them to your friends. All right, any questions about problem set stuff? Anyway, so where things sort of left off was just in dealing with skating, which is a story of inertia, by and large, and issues associated with acceleration, which is the other alternative. Inertia has things moving as they were. Acceleration causes them to change how they're moving. And just, I guess, to finish off the thoughts, skating is a perfectly good topic. I could have chosen coasting on any sort of wheels. Bicycles would have worked, cars would have worked, trains would have worked. All these situations in which you're basically more or less free of friction, more or less free of air resistance, which will show up again today, more or less free of gravity, in the sense that they don't influence the story very much. Things left to themselves, when they're essentially free of those other nuisance effects, they just keep doing what they're doing. They move according to inertia. They are inertial, and they coast. And so skaters do a lot of coasting, particularly if they're not very sophisticated skaters. You get yourself started, and then you coast. The act of starting and the act of stopping are not coasting. They involve acceleration, where your velocity changes with time. In those cases, it's pretty straightforward that you're changing it with time. You're going from not moving to moving, or from moving to not moving. The acceleration is pretty in your face. As came up as a result of the questions last time, you can also accelerate when you change your direction of travel. So basically, any change in velocity involves acceleration. So speeding up, slowing down, or changing your direction of travel. You're changing the direction of your velocity. These are all things that involve acceleration, and they're all caused by forces. You can't accelerate without a force acting on you. So what are other things, just to try to finish the story? So forces cause accelerations. They go hand in hand. You can't respond to all the individual forces acting on you. Instead, you respond, your acceleration is caused by the sum of all forces acting on you. So if you're experiencing two at once or more, you may accelerate in a complicated way, or maybe not even at all. I'm currently experiencing two forces, apart from any little detail ones. There are two big forces acting on me. One is my weight downward, which I'll talk about today, and the other is an upward push from the floor. And those two forces happen to cancel perfectly. One's upward, one's downward. They're quite strong, and because of the way in which things that vector quantities add, when they point in opposite directions, they tend to kill one another off. And they do, in this case, kill each other off to zero. So I'm not accelerating despite having two forces that are quite strong acting on me. They just sum to zero. Is that okay? I finished up last time talking about mass. Mass is essentially the measure of an object's inertia. So a train has a big mass. A mosquito has a little mass. If you're driving along and a mosquito hits your front windshield, it's going to be bad for the mosquito. If you're driving along and a train hits your mosquito, and a train hits your window, the train isn't going to accelerate very much, you are. Okay, so in collisions, the thing with the least mass usually does the most accelerating. We'll talk about the fact that things push on each other equally hard in opposite directions. That's another story for the future. But anyway, little stuff with little masses accelerate easy. Big stuff with big masses accelerates much more difficult. It's much harder to make it accelerate. Any questions about these 5 physical quantities that showed up during the course of talking about skating? Position, velocity, being the change of position with time. Acceleration, being the change of velocity with time. Force, the thing that causes acceleration. And mass, the thing that resists it. Any questions? All right. With that, then, I'm going to move on to talking about falling balls. And falling balls brings into the story, I mean, it's something that happens all the time. Sports are filled with, most sports are built around balls. Many sports are built around balls. And they're often in the process of falling. It brings up the first official force, other than just vaguely just saying, well, there are forces around. And the force is going to be the force of gravity. And the force due to gravity acting on something is also called its weight. So those are exactly the same idea. So this ball experiences a downward force due to gravity. We'll get to it in a second. And that force due to gravity on the ball, which is called the ball's weight. Like any force, it has an amount and direction. The amount we'll talk about shortly. The direction is straight down toward the center of the Earth. That's how gravity works. All right? So it has an amount and direction. And, we'll get to acceleration shortly. Let me start off with my introductory question, my usual thing. Suppose I throw a ball straight up into the air, and we're going to neglect the air again. Remember, I try to set aside the nuisance effects. No friction. We're going to bring gravity in for the first time officially. Up until now, I've tried to bury it. So we're going to set aside friction. We're going to set aside air resistance and other effects due to the air. We'll come to them later in the course, but for right now, we can mostly let them go. So when I throw a ball upward, on its way upward, and when I'm not touching it, when I'm touching it, yeah, I'm pushing all over it. But if I'm not touching it, and it's moving upward, is there any force acting on it in the upward direction, pushing the ball upward? You okay with the question? How many think that, yes, there's a force pushing up on the ball? How many think, no, there's no force pushing up on the ball? Okay, the vast majority are going for no, there's no force pushing up the ball. So why does the ball go up then? You tell me. Inertia. It's an inertia effect. The ball goes upward not because something is pushing it upward, but because it was going upward. And in the absence of gravity, it would go upward at a constant velocity. It would have no force acting on it. It would do what it was doing. So once it leaves my hand and it's heading upward, it wants to keep heading upward. That's its nature. Is that okay with everybody? So we had to, flesh it out more. But the act of falling, we'll see falling, this is falling, of course, and this is falling on its way up. And even this is falling. They're actually not very different effects. I mean, they look a little different. They look a lot different, maybe even. But they're exactly the same process. And in all of these cases, it's a battle between inertia wanting the ball to keep doing what it was doing and gravity pulling straight down on the ball. The gravity is pulling straight down on the ball on its way up, at the top, and on its way down. It doesn't change. I talked last time a little bit about gravity. It came up when someone asked about when you're off in deep space, why objects should be coasting. I I was hesitant about saying that things perfectly coast even in deep space. The question I think was basically, why don't they perfectly coast in deep space? And the answer to that is that there's still gravity around. You can't get away from gravity. It goes to the edges of the universe. The Earth's gravity extends to the edges of the universe. It just gets very weak with distance. Here near the surface of the Earth, it gets weak with distance from the center of the Earth. But the difference in that distance between here and here is tiny compared to the distance to the center of the Earth. That's 4,000 miles down there. That's the effective source of gravity. And to go from this height to this height is just not a big change in 4,000 miles. So the fact that the gravity here is a little stronger than the gravity here, we could forget that. It's tiny. Okay? So we're going to make for today, we're going to make the simplification that gravity is uniform throughout this room, and certainly things even bigger, it's all the same. To further point out the ways in which the details ultimately matter is when I go over here, the force of gravity is straight down here, but the Earth is a ball, and I'm a little bit over on this side of the ball. When I go over here, the force of gravity is straight down here, but I've worked my way around the ball a little bit. So it's not quite the same direction as over there, but the effect is so small. There are people that measure this kind of stuff. It's not my taste in science, but people do this stuff. There are instruments. I'm not sure we've got any in this department. There are certainly instruments that can see the difference between this height and this height. They can measure the tiny differences in distance from the center of the Earth in complicated ways, but they can do it. Okay, so the story for today is the gravity is the same here, there, up, down. The details we can sweep under the rug. Yet another one of those. And returning this question then, when you throw a ball up, there is no upward force acting on it if we neglect air. It's going up not because something's pushing it up, it's because not much is pushing it down hard. Nothing's stopping it fast. So it continues doing what it was doing for a while. It's coasting upward, or trying to coast upward. All right, so some just general observations about falling balls. When you drop a ball from rest, which is, I guess, physics jargon, you start motionless, let go, it begins to head downward essentially almost immediately after you let go of it. There's a little process that's going on, but it goes faster and faster and faster. It acquires more and more speed. If you have any, from time to time people wonder, well, does it really continue to acquire speed? And you know this is the case, because if you put your hand out here for a second, David, if I drop it from here, you're comfortable, right? If I go stand on a ladder and drop it, or if it's a bowling ball, it's getting a little more threatening. Thanks. Okay, so you know from experience, you don't mind somebody dropping a ball in your hand a few inches. You do mind if it's 20 feet. You're a little worried about that because you know it's building up something, and what it is, one of the things that builds up is greater and greater downward velocity. Okay, so what else? When you toss a ball straight up, it rises. It goes slower and slower as it goes up. It reaches a peak, which is an interesting moment. It's not as special as you might think it is, but it seems kind of special. There's a peak height, and once it reaches the peak height, at which moment it's motionless, it turns out, it begins to descend as though you dropped it from up there. So it repeats the first part of the story. And what else? If you throw a ball not straight up, but at an angle, you get this arc. And you may have learned at some point or other that it's the shape of it's got a geometric shape known as a parabola. That detail is not so important as the fact that it's doing two things at once. It is simultaneously falling in the vertical direction, and it is coasting horizontally. And we'll tease that out down the road. So it's covering equal distances downfield in equal times. At the same time, it's rising to a peak and descending as though I threw it straight up and down. The vertical motion is indistinguishable from straight up and down motion. Okay? That's the story. That's what we will go through. All right, so why does the ball fall downward at all? So this is the first question, and I got a bunch of other questions to follow that. Again, I'll remind you, I put these questions, the whole story, those slides on the web. You can download them as you like. All right, so why does a drop ball fall downward? And it's because it experiences a downward weight, which I've talked a little bit about already, that causes it to accelerate downward. So when I let go of this ball, well, while I'm holding it, life's complicated. When I let go of it, it's experiencing only one force, neglecting air. All right? And let me just say, I won't even. Neglecting air is, it's painful for me to keep saying that kind of stuff. I have to do it because I don't want to confuse, I don't want to be sort of legally incorrect. It's like, you'll see them in the questions on the homework, questions on the exam, that I will insert phrases and even sentences that try to pin down things that if I didn't say them, it wouldn't be legally correct. I'd be omitting something and that people could say, wait a second, what about if this is true? All right, so neglecting air. When I let go of it, it's experiencing only one force. Its weight downward. And if an object is experiencing a downward force, what does it do? It accelerates, right? And it's a force that doesn't change with where I'm located within this room, because gravity is uniform. I'm making this assumption, which is pretty nearly perfect, but not quite, that the gravity is the same here, there, everywhere in this room, or maybe even a little bit beyond. When I let go of it, gravity produces a weight in this ball that pulls it downward, and it's the same here as here as here as here as here. So when I let go of the ball, it accelerates in response to a steady downward force. So not only is it experiencing a downward force that's steady, but its acceleration is steady. It's a constant downward acceleration, which means that the change in velocity can't snap. It's the same change in velocity every second. So it accumulates more and more downward velocity, having been dropped from motionlessness. All right? What else about the weight? Nothing else I want to say. I'll reiterate that the ball's weight and the force of gravity, of the Earth's gravity on this ball, they are exactly the same concept, just different names for the same thing. So, all right. So how do different balls fall? So I've got this ball, and what about if I, instead of dropping just if I drop two baseballs, the fact that they build up downward velocity at the same rate and ultimately travel the same distances in the same amount of times, that's not very surprising. They both go down together. What about if I change to a different ball? So I could go to the bowling ball, and there have been times when it has rolled off the table on its own, and the people from downstairs come upstairs to see whether we're okay. If I drop these two, is one going to hit before the other, or are they going to hit together? Yeah, everybody vote. How many think that the baseball will hit first? How many think the golf ball will hit first? How many think they'll hit together? Okay, there are a few votes for the two hitting one before the other, and most votes for together. Ready, get set. Simultaneous. They hit together. Well, that's a weird result. How is that possible? And to show you why that happens, why this ball, despite weighing more than that ball, hits at the same time, or why this ball, despite having more mass than this ball, hits at the same time. So we'll do that. Okay, so first observation is that a ball's weight, which is the force of gravity, force due to the Earth's gravity on the ball, the ball's weight is proportional to the ball's mass. Mass is the measure of the ball's inertia, how hard it is to shake. And I hope you can follow me with the idea that is how hard it is to shake. When you do this with a ball, you are causing it first to head to the left and therefore have a leftward velocity, and then to the right and have a rightward velocity, and back and forth. That involves a lot of acceleration. So shaking a ball is a perfectly viable way of measuring its mass. It's not an easy way to do it technically. It's tough. But actually they have done this to weigh an astronaut. Not to weigh an astronaut. To measure the astronaut's mass. They have from time to time made jigs up there in those spacecraft that shake the astronaut, literally. They grab onto a framework and the framework shakes the astronaut back and forth to see how much mass they have. Because you can't measure their weight directly. It's very hard. You call it weightlessness, but that's a story for the future. You can't just have them stand on a scale. It won't read anything. Okay, so how do you figure out how much astronaut there is there? Shake them. Okay, so this ball, coming back to the story at hand, this ball is harder to shake than this ball. That's mass. This ball is heavier than this ball. That's weight. That's a gravity effect. The fact that they go together, the ball with more mass has more weight, and not a random amount more weight. It's exactly proportional. If this is 10 times the mass of the golf ball, the baseball is 10 times the mass of the golf ball, then the baseball weighs 10 times as much as the golf ball. The point of this harangue is these are very different physical quantities, mass and weight. They're both physical quantities. They're both things you can measure, and they have an amount and units. Mass is a purely inertial story. This ball has the same mass here as anywhere else in the universe. You could take it anywhere in the universe, shake it, it would be the same shakeability. How about weight? Weight is a very local issue. The weight of the ball here on Earth is a certain value. If you took it to the moon or Jupiter, it would have a different weight because the force of gravity would change with where you're located. You're near a bigger planet, littler planet, whatever. So there are different concepts. That, if you remember the first day I asked you, can you distinguish various physical quantities? The first pairing was velocity and acceleration. We've seen that already. The second pairing was mass and weight. Can you distinguish them? Here I'm asking you to distinguish them. We've now done it. Weight is a force due to gravity. Mass is the resistance to acceleration. In other words, the measure of an object's inertia. All right. So if you divide the weight of the ball, pick a ball, the baseball, you divide its weight, middling weight, okay? Divide it by its mass, middling mass. Divide one by the other, you get a certain value. And that value turns out to be 9.8 newtons, that's a force, per kilogram, that's a mass. So the ratio of the ball's weight, this ball's weight to this ball's mass is 9.8 newtons of force per kilogram of mass. That's true of this ball as well. This has less weight and also less mass, so the division's the same. The point is then that if you take any object in this room, yourselves included, you take your weight and you divide it by your mass, you'll come out with the same 9.8 newtons per kilogram. It turns out that every kilogram of mass in this room is given 9.8 newtons of weight. They go together. They go hand in hand. Despite being very different weight, why gravity should care about mass is not obvious. It's a long story that weight and mass are proportional to one another. Got someone you're familiar with, namely Albert Einstein, thinking about, why is that? And he took that to its logical conclusion, and he finally came up with one of his theories of relativity. The so-called general theory of relativity is based on that observation that why should gravity care about mass? Why does it? Yeah. Okay, I'll stop with that. I can go on forever. All right. Questions? Yeah. Harrison's question is, does that have anything to do with the acceleration of gravity, namely 9.8 meters per second squared? And the answer is yes. I will flip back to this. 9.8 newtons per kilogram. Kilogram is a fundamental unit. It is a fundamental unit. You don't write kilograms in terms of other units, pieces assembled. You don't assemble it out of other units. Newton, however, is not a fundamental unit. It is assembled out of other units. And the other units, when you put them in, 1 Newton, it's the force that causes an acceleration of 1 meter per second squared when it's exerted on 1 kilogram of stuff. And when you put that observation, that a Newton is related to meters per second squared and kilograms, you put that together and you shove it in there, the kilograms cancel and the meters per second squared show up. And you end up with 9.8 meters per second squared. It's the same unit as newtons per kilogram. It's just assembled out of pieces. So I'll come to that in a second. That 9.8 is not for those of you who have ever encountered falling things and the acceleration due to gravity, that 9.8 is the same 9.8 because the units, newtons per kilogram, is the same units as meters per second. I'll show you this again. If it doesn't make any sense, ask me and I'll try to do it carefully. We're sort of, yeah, we'll get there. Okay, so having talked a little about this then, if you take various coins, a handful of random coins, there's some quarters, some nickels, some pennies, dimes, and well, I'm not going to drop them yet. Compare the possibilities here. A quarter has the same mass and the same weight as a dime. A quarter has the same mass but more weight as a dime, and so on. Hopefully you can read all those. How many think that the answer, the correct statement here is a quarter has the same mass and the same weight as a dime? Good, nobody votes for that one. How about a quarter has the same mass but more weight than a dime? How about a quarter has more mass but the same weight as a dime? Yay, okay, finally, D, a quarter has more mass and more weight. Yay, tough question. Okay, I'm not ready to drop them yet. I'll drop them in a minute. Okay, to flesh out this story about the 9.8 and the units. This is one of the rare, early on I have to do some calculations, a little bit of calculation. You'll see even these relationships you won't have to remember. I have ultimately only about two formulas that I care that you remember. We haven't come to them yet. The first, one that will show up is what's called Newton's second law. We did see that one. The second one that will show up is the relationship associated with work, and we'll come up with that during the section on ramps. Newton's second law, to remind you, is the observation that if you exert a force on an object, a known amount of force on the object, and it's got a known amount of mass, if you take the force exerted on the object, assuming no other forces, and divide it by the mass, you get the acceleration of the object. That relationship's known as Newton's second law. You should know. You may remember it as F equals ma. Hopefully it has more meaning than just a little alphabet soup. We'll come to work. These ones, hopefully you can bear with me and they'll make sense to you, at least for today. But the point of these calculations is to justify why all things fall together. Okay, so the first of these calculations is simply Newton's second law, that the acceleration of some object is caused by a force divided by that object's mass. So that's this relationship up here is just no light, no joy. Okay. This you can see, yeah. The acceleration of a ball being just choosing an object is just the force on the ball divided by the mass of the ball. So if you exert a known force, and it will be gravity in a moment, and you know the mass of the ball, you divide one by the other, and that's the ball's acceleration. So far, okay? Second observation is, if the force is the weight of the ball, that there's no other force around, then you can substitute for the net force on the ball, you can substitute in the weight of the ball. So there it is. It's now the acceleration of the falling ball is the ball's weight divided by the ball's mass. And I told you about that is the case. That's an observation. This is how it works. And I also told you that if you take the weight of any object and divide it by the mass of that same object, you always get 9.8 newtons per kilogram here near the Earth's surface. And if I didn't use that limiting phrase, near the Earth's surface, I'm sorry. I should have used it. That's the value for around here. It's not 9.8000000. It's not a precise number. It actually does vary a little bit with location, ever so slightly. I think here in Charlottesville, it is about 9.78. It's not quite 9.8, but it's close enough. So just so you know that that's not some sacred number. It's about 9.8, and it's 9.8 newtons per kilogram. That's the acceleration of the volleyball. Now that looks very strange because it's saying that an acceleration, that is the rate at which a velocity is changing with time, is equal to 9.8, a force divided by a mass. That seems strange. It turns out that as I said, is the same unit. A newton per kilogram is also a meter per second squared, which is the standard unit, the SI metric unit of acceleration. So if you convert this newton per kilogram into the other unit, meter per second squared, exactly the same, you get the acceleration due to gravity is 9.8 meters per second squared. The fact that the unit, the standard unit of acceleration, it has this meters per second squared in it. Where does that come from? I don't want to dwell too long on units, but let me just give you a quick version. You remember position? My position relative to that point between the top of this mast here. I'm 2 meters in this direction, south. My position is 2 meters relative to the 0, south. The unit of position is meters. It's a distance. How about velocity? Well, if my position is changing with time, how much is it changing with time? It's changing by, right now, it's about 1 meter per second. My position is changing 1 meter per second. The unit of velocity is the meter per second. Is that okay? More familiar ones would be miles per hour. Velocity has the same units as speed. Speed is just the velocity, just the amount part of velocity without the direction. How about acceleration? It's the rate at which velocity is changing with time. So if I'm picking up speed, which is one way to accelerate, towards your left, I'm picking up about 1 meter per second, that's a unit of velocity, per second. That's 1 meter per second, or 1 meter per second squared. The units of acceleration have this strange character that they are a distance divided by a time squared. A distance being meters, times squared being seconds squared. Okay? So the acceleration due to gravity, just based on just burrowing into the calculation, is 9.8 meters per second squared. What does that mean? That means that if you take any ball, or virtually any object, and you let go of it, so the only force it's experiencing is its weight downward, it accelerates. And the acceleration is 9.8 meters per second. It acquires more downward velocity than it had before, and in a 1 second period, it acquires 9.8 meters per second worth of that downward velocity. 9.8 meters is about 30 feet, 32 feet, and when you let go of it, it goes from 0 velocity when you let go to, after 1 second, moving at 9.8 meters per second downward, or 32 feet per second downward. It picks up speed fast. And you know this from sad experience of dropping stuff. Hopefully not yourself, not very far. But when you let go of things, they pick up downward speed very quickly. the acceleration due to gravity is quite large, and you don't want to fall for more than a few seconds. Okay? So the fact that I didn't have to say which ball experienced this downward acceleration suggests that all balls experience this same acceleration, and the same for all coins. So if I drop a handful of coins, and now I'm at this point, so I'll take dimes, nickels, quarters, whatever. If I drop all the coins together, let go of them, which hits first? The big coins, the little coins, the medium weight coins, or all of them hit together? How many think the heaviest coin hit first? How about the medium weight coin hit first? How about the light coin hits first? How about they all hit together? Yeah, it's all together. Down they go. Picking up pennies. The reason for that is the heavier coins, if all that mattered was their weight, the heavy coin would be pulled down harder, it would hit first. It would accelerate faster and it'd be done. If all that mattered were their mass, the heavier coin, that being the more massive coin, would resist acceleration more and it would hit last. So you've got two competing effects. I'm trying to make sure that this conveys to you. They're two completely different issues competing with one another. This ball, if all that mattered was the ball's weight, it would hit first relative to the golf ball. It's pulled down harder. If all that mattered was this ball's mass, it would hit last because it's more resistant to acceleration. Those two effects, weight, wanting the heavier one to go down faster. Mass, wanting the more massive one to go down slower. They perfectly cancel. And so the two balls go down together. Wow. Or not. All right? Air resistance. Having just said that, if I now drop the golf ball and a sheet of paper, which one's going to hit first? Golf ball wins. So that seems to throw a wrench into the system I've just described for you. Is this a gravity issue causing the paper to get down second? No, it's an air resistance one. And I've been trying to ignore air resistance. So if I could get rid of the air resistance, would the two paper and golf ball hit together? Yeah, sure they would. How can I get rid of air resistance with a ball without... If I got a vacuum system out here, I was talking with Michael before class, that get a vacuum system, you could drop a feather and a ball together and the feather falls just as fast as the ball. So on the moon, feather and ball, there's no atmosphere on the moon. They fall together. How about, can I get rid of the air resistance on the paper? And if you watched what I was doing mindlessly, you would know how I get rid of the air resistance. What I've just done, by putting the book will fall with the golf ball, and you know they'll hit together. It's so massive and so heavy, it doesn't care about the air much at all. I'm going to allow the paper to draft behind the ball. Drafting is many sports involve drafting, that if you're the speed skaters and bicyclists and stuff, if you go in the air, the wake of air behind a person, that air is being dragged along by the person. And if you run in that pocket of air, you experience much less air resistance. This is a topic we'll deal with down the road. But what this sheet of paper is going to do is it's going to ride inside the pocket of air that the book wipes out of the way. And basically, there will be no longer any air resistance on the sheet of paper. Is that okay with questions about that idea? Ready, get set. They all hit together. Book hit. Okay? So everything really does fall together. Air resistance does show up in certain circumstances. If you can get rid of it, they all fall together. All right? What else here? All right, how about on the moon? So we took the ball to the moon. Would it fall the same way? And the answer is no. It would fall more slowly. Why? Because on the moon, the ball has the same mass as before. That doesn't change from location to location. But the force due to gravity, in other words, the weight of the ball, does vary with location. And if you go to the moon, the force due to gravity they're all weaker. The moon has much weaker gravity, in part because it has itself so much less mass. That's partially compensated. It's only like 1/100th the mass of the Earth. It's tiny compared to the Earth, mass-wise. Because it's smaller in diameter, you are closer to its center if you're standing on its surface, and that partially compensates for the moon's dinky mass. Consequently, the force due to gravity on, say, an astronaut is about 1/6 what it is on Earth. So if you were to go there, you would weigh 1/6. I should point out this is a way to lose weight. There are various ways. You know, if you're desperate to lose weight, you can go to the moon and you will lose nearly all of your weight. It's real. You know, it's official. They would have to. You go to a weigh-in or something for some activity, and you're down by a factor of 6. Hey, it's legit. Usually when people talk about losing weight, they really want to lose mass. Measuring mass is harder, so they usually measure weight instead. But losing mass requires actually not eating very much. Losing weight just means go someplace where the gravity's weak. All right. There are easier ways to lose weight than going to the moon. If you go to a mountain, you will weigh a little less because you're a little farther from the Earth's center. And ever so slightly, that will reduce your weight. The difference between, the more effective way of losing weight is to go to the equator. The Earth is not perfectly round. These little factoids of, it's worth it. The Earth is not exactly round because it's spinning. And because it's spinning, it's sort of flung out at the center like spinning a sheet of pizza, disc of pizza. The consequences of that are that when you're on the equator, you're a little farther from the center of the Earth, it being flung out, and your weight is down by about 0.5% compared to if you were standing on the pole of the Earth, North Pole or South Pole. So you can actually lose weight, not very much, but a little bit, and it's real, by going to the equator relative to Charlottesville. All right? Mass won't change. So how do things move? If you drop a ball from rest, this is just sort of fleshing out how you would calculate, if you wanted to, how the ball moves. When you let go of it and allow it to begin to accelerate due to its weight alone, which is what falling means. Falling is accelerating due to weight. A falling object is one that experiences only its weight. That's the only force it experiences. So it's falling. And any falling object experiences a downward acceleration of this number, 9.8 meters per second squared. Generally, that amount is known as the acceleration due to gravity. It's a named quantity. It's a named acceleration. And so the ball will experience the acceleration due to gravity when it's falling. If you drop it from rest, that downward acceleration will cause it to go faster and faster and faster in the downward direction. Nothing more. All right? After 1 second of falling, it will have accumulated 9.8 meters per second of downward velocity. After 2 seconds, it will have accumulated twice that amount, namely 19.6 meters per second of downward velocity. 3 seconds, it's now at almost 30 meters per second downward velocity. It's okay? How does that affect where it's located? So this drawing is an older version from the text. The acceleration is rock steady because it doesn't matter where the ball is or how long it's fallen, assuming it stays within a small region of the Earth. It's going to steadily accelerate downward at the acceleration due to gravity. The minus sign here, incidentally, is it's a simplification that comes if all the motion is going to occur vertically, up and down. Instead of talking about all the vector stuff that comes with being able to accelerate in any old direction, you just simplify things by saying, well, all it can do is go up or down. Let's make that the world of positive numbers, and this the world of negative numbers. And let's leave out all the issues of which direction you're heading. If it's velocity or acceleration are positive, it's doing something in this direction. If those values are negative, it's doing something in that direction. So for a ball that's falling, it's accelerating downward toward the negative world at 9.8 meters per second squared. And it does that whether it's high or low or fast or slow or going up or down, who cares? Doesn't matter. The velocity does matter. With time, it gradually accumulates this downward velocity. It goes faster and faster downward. Every second, it accumulates an additional 9.8 meters per second downward. Position is the complicated one. The position of a falling object dropped from motionlessness, from rest. The position evolves in a funny way. It covers more and more distance each second. So the position starts with small increments per second, and then it gets bigger and bigger increments per second until it's really covering huge distances per second after a few seconds of falling. The consequences of this, if you're going to set up a bungee jumping concession somewhere, if you want people to be able to jump off a ladder or a ledge or something like that and fall for 1 second, it's not too bad. They don't cover very much distance in 1 second because they start that second motionless. They end that second traveling about 10 meters per second downward. And on average, they're in between. About 5 meters per second is their average downward velocity. They only cover about 5 meters in that first second. Not much. You can make a short bungee jumping rig. 2 seconds, they travel a lot farther because that second, they started it moving downward pretty fast already. And they finished it after the end of the second, they were traveling down almost 20 meters per second. So their average speed in that second was about 15 meters per second, 3 times as fast as the average during the first second. In the third second, they travel more, fourth second more. A bungee jumping, if you have gone to some place like King's Dominion, at least used to have a thing where they had 2 big pylons with cords that came out, and they would take people way up in the air and release them and let them. They didn't fall directly down, but they fell at an arc. Do they still have that thing? It's a couple seconds of downward plunge. That's all they can do because with each additional second they want to have you plunge, you have to cover way more distance. So 2 or 3 seconds they can handle. 6 seconds, 7 seconds, this thing would have to be skyscraper tall because you travel so far in the 5th or 6th or 7th second. So that's the limit on those. All right, this is the story of dropping from rest. I'll finish up on Wednesday with the idea of a falling object that was starting upward and all the way a falling object that was traveling at an angle.